Look at that. Thank you guys for missing Surefire Live to be here. Okay, so this is class number 1 for the Master's Services CSIA exam prep. I just wanted to thank the guys that got on here and lady. Hi, Gina. We are going to be going over everything beginning to end that we need to know about vented appliances, chimneys and fireplaces, and fuel burning appliances. So where do we begin? We have to know exactly what constitutes a chimney, fireplace, or vented appliance, correct? So just like we explained to everyone else, a vented appliance is going to be any appliance that is going to vent fumes, gases, and other noxious or caustic materials. We've got stoves, we've got type 2, 3, and 4 appliances. We've got the A and B classified fireplaces. So that's going to be your class A units, or like your standard prefabs or masonries. And then your class B units are going to be your B vents and your direct vents. So when we talk about chimneys and fireplaces, what exactly are we talking about? So when we are looking at a chimney or fireplace, which is the majority of our business, so that's really where we're gonna focus a lot of our attention, is 3 main components. And the educators at Master Services all know that there are 3 main components to a chimney and fireplace. And we have our dance moves, right, Marty?
Yep.
All right. So 3 main components to any chimney and fireplace is, hands up, firebox. The firebox is where we burn the fire, right? Above the firebox, we have the smoke chamber. That's going to be your A-frame. And then above that is the flue, right? All right, educators, ready? Firebox, smoke chamber, flue. Firebox, smoke chamber, flue. Now, what does the National Fire Code really concern? It concerns containment. It concerns containment of all of the excessive heat, spark, the actual fire itself, carbon monoxide, carbon dioxide, excess creosote, and water vapor that is a result of combustion within the firebox. So how do we know what it is that we're looking at? So in the test, it's going to be referencing both prefabs and masonries. So we need to know the difference between the two. A masonry is any on-site built chimney that's built out of a non-combustible masonry product, like brick or stone and mortar. That's from the ground up. That's what a masonry chimney is. Your prefabs, or manufacturers prefabricated, factory built fireplaces, are going to be all of those fireboxes and flue systems that are built in a factory, delivered on site, and then assembled, much in the way that you would Legos. So we'll have the steel firebox and all of the flue pipe, including the spark arrestor, storm collar. We'll do chase cover, and they generally are a wood frame chimney with some form of siding or masonry around the chimney. So those are going to be our 2 different types of fireplaces. Your class Bs and your direct vents are both prefabricated units. But when we talk about just a standard prefab, we are talking about the class A vented units, which are those standard wood burning prefabs that we install and inspect every day of the week. So getting down to the nitty gritty of it, when we are talking about chimneys and fireplaces, what is it that we are inspecting, right? We are looking for containment 100% of the way. We don't want any gaps. Does anybody know the maximum allowable gap or the minimum allowable gap that requires repair or replacement of a product? It's 1/16 of an inch, roughly the thickness of a dime. And you're going to see that come into play if we have anywhere within a flue system or the firebox system that there are failures that are 1/16 of an inch or more, that part either has to be repaired or replaced. So in the case of prefabs, in the refractory panels in a prefab, if we do have a crack or damage to the prefab that's 1/16 of an inch wide, roughly what you could put a dime into, or if it's abraded 1/4 inch down from the surface, those panels are going to be replaced. The same in the factory flue piping. If we notice separation of 1/16 of an inch, if you could fit a dime in between the two sections of flue pipe where they come together, that needs to be repaired or replaced. And generally with those flue pipes, there's not going to be a great way to just repair that inner flue pipe without ripping the whole thing apart. Something to know about those prefabs is it is a mechanical connection. Once it goes together, it's not truly meant to come back apart. So you are going to end up tearing it apart to try and get down and fix that inner piece. In the case of masonry fireplaces, if we are inside of a firebox and we see cracks that are 1/16 of an inch wide, we will repair that with some minor tuck pointing. If we see cracks or separation in the flue, we will reline it with either a stainless steel drop-in liner or our thermocrete system that we use. So let's try and get into it, and let's cover some questions, and we're going to do the whether twos and why fours of these questions. And thank you to Corey, who spent the better part of his day today while we were driving around sitting with the Chimney Inventing Essentials book from the CSIA, and he was looking at our review questions and he was writing down page numbers. So if anybody has any questions about why something is or what something is, we can look that up here. So when we are talking about chimneys and fireplaces, one of the main things that we want to concern ourselves with is the draft. So what is the draft? The definition of draft is the difference of pressure inside and outside of the venting system. The venting system being our three components: firebox, smoke chamber, and flue. So it's the pressure differential between that. Higher pressure at the base and lower pressure at the top means that everything is going to want to push up and out of the top, creating the draft. The definition of draft, thank you, Corey, we just covered. So draft is measured by inches in the water column. So here, I should really put tabs in this book for when we cover it. Measuring chimney draft. Draft is measured in inches in the water column. Most technicians are familiar with the concept of air pressure. The tires on your truck may call for 40 psi or pounds per square inch, or they may require 60 to 70 psi. When pressure drops below 1 psi, it is commonly measured in inches of water column. There are nearly 28 inches of water column in 1 psi. When the pressure drops even more, it is measured in pascals. There are 249 pascals in 1 inch of the water column. So when we're measuring draft and we're talking about measuring into the water column, we're not actually talking about putting something in there full of water to try and measure for it. What we're talking about is something less than 1 psi or 1 pound per square inch of pressure. And we're just going to work our way through these review questions. These are the questions that are on the Quizlet that I shared earlier. And I will tag the Quizlet in the recording as well when I post it. I'll post the videos of these when we do them onto Connect Team, and they'll be posted on YouTube, so anybody can pull them up and watch them at any time. So these questions are going to kind of jump around. So just be prepared that they are going to go in the order that they're in. They're not in any one particular order. So back puffing is the next question. The easiest solution to resolve back puffing on a stove. So wood stoves are the cast iron wood burning units that radiate heat out at a greater amount than just your standard fireplace. A lot of people prefer them because of the amount of heat that they put out over a standard fireplace. So if we're getting back puffing from the stove, meaning that we're getting smoke back into the home, how do we resolve that? Well, number one way we're going to resolve that is by adding one of the three things needed for proper combustion. Those three things are going to be heat or ignition source. It's going to be some kind of a fuel, which would be the wood, and it's going to be oxygen. So one of the ways to resolve back puffing is by creating a higher pressure situation in the firebox, and we're going to get that by adding more air. So we're going to resolve back puffing by adding more air. And if anybody has a question about any of this, all you have to do is just raise your hand and we'll stop and we will re-engage. What has the greatest effect on flow, and what is flow? So we've already talked about draft. Draft is the pressure differential. Draft is not the air moving up, it's the pressure differential between the inside of the venting system and the outside of the venting system. Flow is the actual movement of material through the system. So what starts in the firebox moves up into the smoke chamber and then through the flue and out the top of the chimney. That is our flow. The greatest effect on flow is going to be the size of the venting system passageway or the flue. So if you have a narrower flue, you're not going to push as much smoke and gases and creosote and everything else up and through the chimney as if you had a wider flue. Now, that is to state, if your chimney is below 22 feet, we're going to get into flue sizes here in the next couple of videos, but there are calculations to know what size of flue you should have, but having an undersized flue is definitely going to decrease your flow. A masonry chimney is required by what code to have a clean out if the flue previously vented a solid or liquid fuel appliance? So if the system that you're working on is currently or has ever worked with a liquid or solid appliance, it needs to have an ability to be cleaned out. So this is actually very important. With our B-vented appliances and our direct vent appliances, if any of you have ever seen those, when you look up into the fireplace where the damper normally is, right where the flue opens, there's generally some kind of a shield there at that point. That has its own purpose for being there, but at the same time, it's restricting you from running a brush at that point because it's only a gas burning appliance. It does not need you to have access to sweep at that point. Now, with your standard prefab or a masonry, or let's say an oil furnace or a wood stove, we have to have some point at which we can sweep out that unit. So who tells us that we have to have that area, that clean out space for us to be able to clean out? And that is the NFPA. Now, here's the deal. The NFPA is going to be referenced many times for this. We follow the NFPA 211 on our day-to-day business. The NFPA 54 is the National Fuel Gas Code, and the NFPA 54 is the correct answer. So according to who do you have to have a clean out if your flue previously vented a solid or liquid fuel? And that is the NFPA 54. That is the National Fuel Gas Code. So if you think about your standard masonry chimney, we will have an ash dump door and clean out at that point, and we will also have the damper that we can get through with a brush and clean at that point, and it allows all of the solids to be taken out there. In the case of wood stoves, we'll have the pipe that generally has a T-space in the pipe. On the outside, you walk to the outside of the house, you open up the bottom of the T-space, and you run the brush up and down, and everything falls right there onto the ground. Holy cow. Sorry. Phone's going crazy. All right. High efficiency gas and oil appliances generate a lot of what? Which can what? Now, anytime that we burn, in a perfect burning scenario, the two things that we are going to get in burning is going to be carbon dioxide and water vapor. Why is that? When we burn, we are going to be off-gassing carbon, hydrogen, and oxygen. When you burn, those molecules are going to get slammed back together, and they're going to get slammed back together in different ways. So on one side of it, when it burns and it hits a certain heat point, a carbon and an oxygen molecule are going to collide, and they're going to create carbon monoxide. As that continues to churn and burn within the system, it'll hit another burn point, and another oxygen molecule will get added to it, and that creates carbon dioxide. At the same time, you'll have hydrogen and hydrogen and oxygen molecules that will collide, and that creates H2O, or hydrogen dioxide, which is water, and that's the water vapor. So in a perfect burning scenario, we're already going to be creating carbon dioxide, we're going to be creating water vapor, and we're going to be creating an excess of heat. So high efficiency gas and oil appliances are going to be creating water vapor. And why is that bad? That's because water is like cancer to chimneys and fireplaces. Whether it's a prefab or a masonry, it doesn't matter. Water is like cancer. And the reason is that with the prefab systems, they're made of steel, and steel is going to rust. With the addition of the caustic creosote buildups, when you add the moisture and the creosote, it's going to start to rust and eat away at the steel. In the case of masonry fireplaces, the water is going to be absorbed into the pores of the brick and mortar. And whether you're using the fireplace or not, it doesn't really matter. It's going to be the temperature thresholds. Either ends of the temperature spectrum, water wants to do the exact same thing. It wants to expand to escape. So if I'm sitting in a room right now that is either too hot or too cold, and the next room over is a perfect climate, I'm going to want to get up and go to that room. So if this room's too cold and the other room is sunny, I'll go sit in there. If this room's too hot and the other room is shaded, I'm going to want to go sit in there, so I will get up and I will move. We're 78% water. And that's the thing to remember, is water wants to do the same thing. It expands at both ends of the temperature spectrum. So if you're using the fireplace, or if it's just an extremely hot summer and those bricks are just getting baked one way or another, that moisture is going to convert to steam as it evaporates, and it's going to try and escape the pores of the brick and mortar. As it expands, it's going to blow out the mortar, it's going to crack brick. You'll see flue translation in those terracotta flue tiles and in the fire brick within the flue. They'll start to move as the mortar starts to break down. The interesting thing is, like I said, at the other end of the temperature spectrum, when it freezes, it does the exact same thing, but this time it converts to frost. And as it freezes and expands, it will do all of the same damage in all of the same way. So the way that I like to explain it to people is, imagine taking a water bottle and putting it in the freezer, and it's going to expand and it's going to blow the lid off of it. And that water bottle will get swollen up and it may even crack the water bottle. Now, if you take the same water bottle and you put it in the microwave and you set it for 4 minutes, it's also going to expand because of the amount of pressure from the steam, and the water bottle will explode. And again, you'll get water that goes everywhere. So in a high efficiency gas and oil appliance, they generate a lot of water vapor, which can deteriorate a chimney quickly. Whether it is steel or whether it is masonry, it does not matter. It will either rust it out or it will degrade that masonry product: brick, mortar, stone, cinder blocks, concrete, whatever. The information about use and installation of a gas appliance draft hood can be found where? And again, we're going to go back to that NFPA 54. Most products pertaining to gas are going to be covered under the NFPA 54, which is the National Fuel Gas Code. So when we're referencing something that has direct attention of the National Fuel Gas Code, if it asks that question, it's going to be that. So if it states, where would you find instructions for the installation of a hood for a gas appliance, that references only a gas appliance, it's going to be the NFPA 54. Where can you find venting requirements for category 2, 3, and 4 appliances? And that's very easy. When it's asking where you can find the requirements for a specific product, the best place to find it is the simplest place to find it. It's going to be in the manufacturer's installation manual. Glazed creosote results from 3 things. And what 3 things does it result from? It results from a slow, smoldering fire. So if you've got a very low and slow fire going, you're not going to create the amount of heat and the amount of pressure needed to really push everything up and out of the system as needed. You're not creating that flow, that positive draft, that positive pressure to push everything up and out. Too many bends, turns, or elbows in the system. Every time that we have a turn in a system, what we call an offset, it's going to create a slowdown point. If we're slowing down the flow, we're increasing our residence time. And we'll get to residence time here in a minute. But we're increasing that residence time, which is the amount of time that the smoke and noxious gases are staying within the venting system, what we call the flue. So as we're slowing that down, that smoke wants to linger. As it lingers, it meets the third item, which is an improperly sized vent or improperly sized flue. So if it's too small or too large, it's either going to have cross drafting or it won't be able to draft fast enough. A slow fire is going to push it up and out fast enough. And if there's too many elbows, it's going to slow it down and it's not moving fast enough. Now, creosote in itself is a mixture of multiple things. It is tiny little slivers of wood that were too light to stay where they were, and just the pressure created by the fire is pushing it up into the air. Tiny little splinters, very small splinters of wood. It's also going to be all of the oils and the tree sap that didn't get burnt, as well as some of the ash and the soot that comes from burning the wood. When all of that mixes and gets pushed up into the system, and it'll blend with whatever water vapor that you've got in there. If you don't have enough force to keep that vapor expanded as a large gas and to keep it moving up and out, it's going to slow down. And as it cools, it's going to want to glob together. and it's going to turn into those little globs of creosote. Now, creosote comes in 3 separate stages. Stage 1 is going to be the loose coffee grounds that we sweep out every day as chimney sweeps. It's just those standard loose coffee grounds. You know, if you think Mary Poppins and he's got the soot all over his face, that's exactly what stage 1 is. Stage 2 creosote is that glazed creosote. It's when it actually begins to vitrify and it becomes a glazed on layer, like seasoning on a cast iron pan. That's exactly what that is. Stage 3 is when it starts to build up that glazing. If you've ever seasoned a cast iron pan and you get too much oil in there and it starts to burn and then it gets thick and gooey and drippy and tacky, that's what stage 3 creosote is. So when we start to see that run like tar, that's stage 3. Stage 2, like I tell everyone, when you put your camera up there and you're looking at it, you can twist your camera left and right and you get all the twinkles. I call it diamonds in the sky. When you get that, that's your stage 2 creosote. And then stage 1 is the loose coffee grounds. So we have 3 separate stages of burning. Stage 1 of burning is what we call drying. So what happens in the drying stage? The drying stage is when you're trying to build up enough heat to actually ignite the wood. Ignition comes at the 2nd stage. But in that drying stage, any additional moisture that's left within the wood that you're actually trying to burn is trying to steam off. Something to remember with that is the word steam. We're automatically putting that water up into the firebox, up into the smoke chamber, and up into the flue. When we're doing that, we're adding moisture into the system. That's why we always recommend a very well seasoned, dried wood. The reason we want it dry is because we want that moisture content to only be somewhere between 15 and 25%. That's something that you need to know. Suggested moisture content of the wood is between 15 and 25%. With that, once we get into that drying phase and we start to steam off that excess moisture, we are expending energy. You're expending that precious energy of your fireplace, of the fire you're trying to get built, is being dumped back into now trying to dry the wood that wasn't dried properly to begin with. So it takes longer to build that fire. And because it takes longer, you're noticing the smoke linger more. And that's why green wood seems to be more smoky. It's not so much of any one thing other than the fire itself isn't really hot enough to push it up fast enough that you're not really recognizing it. Some of the smokiness is going to come from the oils and steam from the actual, from the drying process. But that's the drying phase. We're trying to get the wood ready to burn. That's going to be stage 2. Stage 2 of our burning process, or stage 2 of combustion, whichever you prefer to call it, is going to be pyrolysis. So what is pyrolysis? Pyrolysis is the chemical change that happens to the fuel once we burn it. That's pyrolysis. It's taking that wood and chemically altering it so that it is a combustible material in the moment, right? That's pyrolysis. It's the oxidation of the fuel during the combustion process. Now, once we're oxidizing it, we are then moving it towards our carbonizing phase, which we call charcoal. So our 3 phases are drying, pyrolysis, and charcoal. Once we hit the charcoal phase, that's when the wood becomes black and it starts to glow. That's where your embers and your coals come from, is that last and final stage of burning. We already talked about creosote, residence time. I believe I already covered this. Residence time is the length of time the smoke remains within the chimney. So from the time it first builds at the top of the fire until it exits the top of the flue, the amount of time it takes that smoke to go from there up and out of the flue, of the top of the flue under the cap, is your residence time. and we want that time to be as short as possible. Referencing magnetic thermometers. Magnetic thermometers are only going to display about 50% of the actual flue temperature. I'm going to be perfectly honest. I don't know why. I think magnetic thermometers are referencing another thermometer used for stoves and the oil burning furnaces that we don't really get into. So I haven't read enough to know why. Why should creosote be removed? It's a very good question. Creosote should be removed. Number one, because creosote only requires half the heat that the initial fuel required to begin the combustion process. So let's say you've got a log of wood and it takes 900 degrees to catch that log of wood on fire. That means that the creosote produced by that log now only takes 450 degrees to ignite. Now, we've already gone through the stages of creosote. Creosote is the #1 leading cause of chimney fires in the world, anywhere. #1 leading cause of chimney fires. So we need to sweep it out. Number one, it is a fire risk because it is so flammable. Number two, as we've already talked about earlier, creosote is very corrosive to both steel and brick and mortar. It's also corrosive to any connectors that might be in the system. So creosote is very caustic material. It's dangerous to inhale and breathe, and it's also extremely flammable. So it does pose a fire risk. So when it asks why creosote should be removed, #1 answer, it's a fire risk. #2 answer, it damages brick and mortar as well as steel. And #3, it's a caustic material, meaning it's hazardous for us to breathe in and ingest. Next question, why should flashing be embedded in mortar? So on the chimney and roof line, where the chimney comes through the roof line, some people will take a grinder and cut a slice up the chimney, and then they'll stick the flashing in that, and that cut will go across all of the brick and mortar joints. And then they will either caulk or seal it into that point. Although technically it'll work, the best way to do it is to do step flashing on the sides coming all the way down. And as you're building the chimney, you're going to mortar that step flashing in. The reason for that is because when you mortar it in, you're form fitting that flashing to become part of the chimney and not to become an addition to the chimney. And it makes it watertight. It's going to give you an overall better seal against moisture penetration. Hey, Adam. All right. Be perfectly honest, I wish they'd make a test that doesn't have anything to do with oil boilers for us. You know, a Song of the South version of the CSIA test, I think, would be great. Baffle, location, and purpose. Now, I don't like the answer that it gave on the Quizlet, and I actually got a better answer. And it was right here. So the baffle, location, and purpose. On our Quizlet, it talked about fireboxes, and I didn't think that was correct. So I looked it up, and the baffle is not located between the firebox and flue. A baffle is an object that is placed in an appliance to change the direction, extend the path, or slow the flow of air, air-fuel mixtures, or flue gases. It is located between the firebox and stove outlet. So that is a stove question. In the Quizlet, that is one to know the correct answer to. because it talks about how it's installed in between the flue and the collar. That is incorrect. It is installed between the firebox and the stove outlet.
Hey, Cody,
Yeah.
can you explain the purpose for it again?
Yes. Happy to. The purpose is to change the direction, extend the path, or slow the flow of air, air fuel mixtures, or flue gases located between the firebox and it is located between the firebox and stove outlet. I'm sorry if I have to read this stuff twice. I'm not wearing my reading glasses because, you know, I'm the smartest guy.
Thank you.
You're welcome. Okay. And then the next one, it was the same thing. It was the very next answer on here. I didn't like on the Quizlet, the next question was, what does the barometric draft regulator do? I didn't like that one either. The answer was prevents excessive draft. The barometric damper, let's see here, make sure I'm reading this correctly. Yeah. Barometric damper is a device that regulates the draft and prevents excessive draft in a fuel burning appliance by admitting a controlled amount of air to the venting system under normal burning conditions. So it prevents an excessive draft. So it prevents too much pressure within the flue by admitting outside air into the system under normal burning conditions. That's how I'm understanding it. Is that correct, Adam?
Yeah, you know, when you see the prefabs that have it almost looks like a direct vent where it like leads outside and it's got a little vent on the side of the actual prefabricated unit that you can flip open and closed. That's what that is. So yes, you're correct.
Okay. So that's your dryer vent connection. Essentially. You know what I'm talking about on the prefab chimneys? Are you talking about like on the prefabs where when you're looking at the hardy board and there's what looks like the little dryer vent outlet on the side of the chimney?
Exactly. Yep,
and
exactly.
Go inside and there's the extra little damper on the side of the firebox and you can open and close that. Okay. So I'm not going crazy. I know what I'm talking about.
Yep, you would be correct.
Okay. We're going to pass this test one way or another, people. Tune in. Film at 11. Okay. So, by the way, we should all be very thankful that we have Adam here. He has already passed this test, and he is a very good resource. If you're studying and you get stuck on something, Adam said you can call him 24 hours a day. He loves 3 a.m. phone calls. So, all right. This next question I got completely wrong, and I told Corey that when he gave me the answer that was on there, I told him the answer was wrong, and I grabbed my copy of the Chimney Bible and I said, I'm going to look it up and I'm going to show you you're wrong and that the Quizlet's wrong. So here it is. The smoke chamber height, remember, firebox smoke chamber flue, the smoke chamber height shall not be greater than the blank of the fireplace fire chamber. I don't like the wording of that, so I'm going to change the wording of it. The height of the smoke chamber shall not be taller than the width of the fireplace. I said it was the depth of the fireplace. And I've talked with people before, and they have said the depth of the fireplace. But I am telling you guys, I was dead flat wrong. Let's see here, 3.3.
It's
Thank
on
you.
some of our surefire trainings too.
I think it was 3.3.56, if I remember correctly. Or was it 3.1.56? Corey, did you write it down? 3.
I should have wrote it down, but I don't know for sure if I did or not.
But yeah, no, it was I don't see it on here. You know, I should have just kept looking while I was right here instead of just assuming I knew where it was. You know what they say about assuming? It makes an ass out of you and me. All right. 3.3.118. Three, 3.19.
I think it's 11.2.1.11.
11.2.1.11, Marty says. That's why we're here. 11.2.1.11. Whoa. Yep, there it is. It says the smoke chamber height shall not be greater than the inside width of the fireplace room opening. That's very misleading as well, because the fireplace room opening, if I were a homeowner or just some basic dumbass reading this, I would think, man, I can make the smoke chamber as tall as the room is wide. My room's 25 by 14. Hell yeah. You know, and then make a 2.5 story tall smoke chamber. But it's the width of the firebox. So I'll show you here. Bam. So W is equivalent to the width of the firebox, and H is the height. Can you see that?
Yep.
So the height of the smoke chamber is less than or equal to the width of the firebox. So H is less than or equal to W in that scenario. And the most, when we do our little smoke chamber thingy, when we do this, guys, this angle cannot be greater than 45 degrees. So it can be less than 45 degrees, but it cannot be greater than 45 degrees. And remember, the angle is measured at this point off to the side. As we wrap back down, that angle is going up. As we go up this way, the angle goes down, right?
Mhm.
So, okay.
And the reason being is because it messes with the cooling of the gases, correct?
Well, that's the thing, is if we're up like this, we're not really creating a lot of pressure. So we don't want it to go straight up. That doesn't do much of anything for you. The whole point, when we have our firebox, we're burning here, right? And then the smoke chamber is that upside down funnel. Now, anytime you restrict the flow of something, you're increasing pressure. If we're increasing pressure at this point, it's going to go straight up. Now, if we're doing this, we're opening it more, we're going to reduce the pressure. If we're doing this here, we're still reducing the pressure in the flue because we're creating too much pressure in the firebox. So 45 degrees is pretty much right spot on where we want to be. It can be a little wider than that, but 45 degrees, we don't want any tighter than that, because then we're just burning on the bottom side of the brick, even if it's parched. We already talked about the requirements for combustion, which is heat or an ignition point, oxygen and fuel. Nominal dimensions. So nominal dimensions is ish. I think that's a great way of putting it. When you say a nominal dimension, you're saying what's the nominal dimension for a withe? And we'll get into a withe here in a minute. If you say the nominal dimension is 4 inches, then you're saying, hey, how thick should that brick layer be? Yeah, 4-ish inches. Now, what's the sway on that? The nominal means that it has sway. That's the ish. So a nominal dimension is variable by up to positive or negative 1/2 inch. So if you say 4 inches, if you say my nominal dimension for this is 4 inches, you're really saying anything between 3.5 and 4.5 inches. You want 4, but you take 3.5, or you take 4.5, but 4 is really what you want. That's nominal. That's just a great way to put it. 4-ish. I think that's good. So that's nominal dimensions. Let's see here. What is combustion? We already covered that. Combustion is the rapid oxidation of fuel producing heat and light. Let's go over that again. Combustion. Combustion is the rapid oxidation of fuel producing heat and light. So as we're burning something, we're getting heat and we're getting light. So like when you burn a candle, when you burn, when you burn your ex's clothes in the front yard, right? Not their dog. I'm not condoning that. But you kick them out of the house, you put lighter fluid on their clothes and you hit it, you could stand out there and stay warm, and it's going to light up the whole neighborhood, All right. Parging the smoke chamber improves flow by what? Number one, let's talk about the dang smoke chamber, okay? When we're looking at a smoke chamber, we want a nice, smooth smoke chamber. And the reason we want that is because it has good flow. Remember, draft is the amount of pressure, flow is the amount of movement, and residence is the amount of time it sits within the system. So those are the three things that we're really dealing with here. So why does a smooth smoke chamber increase the flow? That's because when a smoke chamber is built, it's built through a process called corbelling. Now, the corbelling is when we take one brick and another brick and another brick, and we get the upside down staircase, right? So how do we resolve this, and why is this such a bad thing? Number one, as we are burning and we get all of the soot and we get the smoke and everything else, the noxious gases, the carbon dioxide, carbon monoxide, the water vapor, everything else, the excess of heat that is coming up off of that fire, as we're getting all of that rise through the top of the firebox, through the damper, and up into the smoke chamber, now we need to funnel it down to fit the size of that flue. So why do we need it to be smooth? That's because when you have corbels, this is the face of a brick, this is the bottom of a brick, and another face of a brick is here. When it's corbelled to create that upside down staircase, that's how we stack it in, just like that. As the heat and everything is rising, it's going to rise, it'll hit the bottom of a brick, and it'll begin to travel. And as it travels, it's going to start to cool down because it's not being pushed up anymore. It's slowed down. And as it slows down, it's going to condense. And as it condenses, it's going to cool. So we're traveling here. It's condensing, it's cooling, it's condensing, it's cooling, it's condensing, it's cooling. As it cools, it becomes heavy. Those gases are now condensing and they're becoming heavy because that water vapor is now starting to shrink something closer to room temperature. So it condenses and it becomes heavier and it starts to drop down. And then we get mixed up with all of this superheated air that's down here at the bottom. And all of a sudden it expands again. And when that happens, it gets pushed right back up into that same system. And it's going to continue to do this over and over and over and over. And if you see that circle motion that my finger is making, that's because it is creating turbulence. It's going to turbulate on the bottom of each of those step outs going all the way up. And sometimes when you get the camera up in the smoke chamber, you'll actually see these rounded points on either side of the smoke chamber at either end of the bricks. You'll see this curvature. That's physically where the air churning is starting to scrub away at the creosote deposit that's there at that point. Why is that bad? If we're creating turbulence at each one of those points going up, we're not pushing enough product up and out. That's going to create a heavy creosote deposit. By slowing down the flow and not pushing everything up the way that it should, everything's going to cool, condense, the water vapor mixes with all of the little bits of everything that creates the creosote, and the creosote creates the deposits. And as those deposits form, it'll travel through the stages, stage 1, stage 2, stage 3 of creosote. In the smoke chamber, because we're bottlenecking everything, we're increasing the amount of pressure. When we increase the amount of pressure, we can increase the amount of heat. When we increase the amount of heat, we can actually get those bricks in there glowing red hot. And they can actually get hot enough to ignite combustible materials that might be nearby. So the 2x4 framing within a home, or maybe some loose shingles or wood that got dropped in the last time they replaced the roof, or anything like that. So we want to come in and we want to parge the smoke chamber. With this step out, we'll add 1 layer of parging, 2 layers of parging, 3 layers of parging, 4 layers of parging, 5 layers of parging, until we get a nice smooth face of that. Now there's different ways of doing it. There's some products that we can just slap in there by hand. You can use a gun, you can brush, and there's multiple different ways of getting that nice smooth texture. But the whole point is we want to cut this corbel out and we want to make it smooth. By making it smooth, as everything starts to rise, it's going to hit that smoke chamber, flow right in, and go into the flue and up and out the way that it should. So why is parging your smoke chamber going to increase your flow? That's because you're reducing turbulence by eliminating the corbelling. And the corbelling is what causes that turbulence. All right. Connector dampers should not block greater than blank % of the connector when closed. Now, this is another one that I have no idea why, and I'm going to have to look at it and figure out why, but it should not block greater than 80% of the connector when closed. That's the correct answer. I found the correct answer in the book. Now I'm trying to get the why so that we can go over it next time. And
Hey,
what
Cody.
we're going to do, yeah, what?
I was thinking about that earlier. Could that have anything to do with like a damper clamp on the damper?
No, that's damper clamp.
That's not. That wouldn't have any connection to this.
No.
Only 80% instead of 100.
No.
Okay.
No. Connector dampers. Connector dampers. I don't even know what a connector damper is, to be perfectly honest. We're all here learning together, man.
It looks like it's that plastic damper that allows the airflow when I typed it in Google.
Connector damper.
Yeah.
Connector. Maybe that's damper types. No, I have flue gas damper, manual operated damper, damper definition, and automatically operated damper, which I know those. Damper connector. I'll get the answer to that one and I'll come back to it. But the correct answer is the connector dampers should not block greater than 80% of the connector when closed. So that's the correct answer. Heat reclaimer extractor. So a heat reclaimer extractor fits in line with a connector and is not to be used with wood burning. So does anybody know what a heat reclaimer extractor is? No? Okay. So like They have water heaters now that have heat reclaimers. And what it does is it pulls ambient heat from inside the room and uses that to heat the water. So as it pulls that ambient heat from in the room, it'll heat the water with that, and then it only has a supplemental burner. So it keeps the water within the water heater at a higher temperature than what's in the room by constantly pulling in the heat, absorbing the heat and pushing out a cooler air at the exhaust. So it's drawing in that heat. So a heat reclaimer extractor is something that we're going to use. The Heatilator steel fireboxes. You guys all know what I'm talking about. It's that steel firebox inside of a masonry that when you look up, there's the tubes that are going, and they've got the light switch on the wall. You flip the light switch and you hear the fans going. That's a heat reclaimer extractor. So as the heat is going up and it's heating that firebox and it's heating those tubes, it's blowing the cool air from the room. It generally draws air in at the bottom, takes it through that system, and then pushes it out of the top. And that air has now been heated by the time it circulates around that firebox. So that's an example of a heat reclaimer extractor. A lot of times you're going to see them, probably what this one is referencing is one that goes on a stovepipe or on some type of a gas appliance where the vented gases are traveling through, and this is going to go around that pipe and it's going to circulate air around the pipe. I know I've seen some where the heat reclaimer extractor will be a pipe that comes up and it travels through a barrel of water and then goes up. So as that flue pipe, as those flue gases are heating up, they'll get that water to pretty much boiling temperature. And then even after the fire goes out, that water will still be hot and radiating heat inside of that secondary container out. Or sometimes they'll use oil. Sometimes it'll just be air that expands, and they'll send the pipe through through that, or it'll just be a fan that simply blows air around that flue pipe that keeps the flue pipe cool, but pushes all the excess heat off of that flue pipe and back and into the room. So heat reclaimer extractor, trying to get as much heat from the flue gases as possible to push excess heat back into the room so that you don't lose any going up and out of the flue system. I'm not crazy, right, Adam? That's exactly what that is. Okay, thank you. By the way, Adam, I'm gonna tell you right now. Here you go. Twinsies.
Yeah.
Everyone else is losers. All right. Okay. So this one, best I can tell, is also dealing with stoves. What inspection level determines if a wall pass-through is installed properly? So a wall pass-through is generally like on a wood stove, when you see them where the stove is sitting in the corner and the pipe comes up and it turns and it goes through the wall, and there's that steel plate. The steel plate has one pipe that comes this way, the outside piece has another pipe that comes and slips over that. And what level of inspection, remember we have 3 levels of inspection, what level of inspection will tell you if that wall pass-through is installed properly? And 2, Adam. 2. Because you don't have to destroy anything. All you have to do is loosen a couple of screws and pull it apart to see if it's installed correctly.
Oh, okay. True. Yeah, that's a good point. I was pulling that whole thing apart to find out.
Yeah. Level 1 inspection. Level 1 inspection. Mark 1 eyeball, digital camera, flashlight, crawl around, look at the places you can get to, get up on the roof with a ladder, look around the chimney. Level 1. Level 2 is the addition of the video camera going up the flue and anywhere else that you can get that camera to inspect those areas without destroying anything. Level 3 is when we call Marty and we get him to come down with the sledgehammer and he starts busting open walls to see if the fire breaks are installed correctly. So, way to go, Demolition Man. All right. Now, this next one, hearth stove. A hearth stove should only be connected to what? And by saying hearth stove, I'm assuming they're talking about a stove insert. The word insert should automatically give it away. A hearth stove or a stove insert should only be installed in a properly built masonry fireplace. Now, here's the deal. You get to somebody that has a stove insert and they've pulled it out for you to inspect it. That is just a masonry fireplace with a stove insert. So if you are inspecting the masonry fireplace and the back wall needs to be rebuilt, lintel needs to be packed, smoke chamber needs to be purged, anything like that, regardless of the fact that they're using a stove, they need a properly built masonry fireplace for a stove insert or hearth stove. Okay. Next. Now we're getting close. Oh, we started about 5 minutes late, so we'll do one more question and then we'll pick back up on Thursday. What problems are created when mortar joints between flue tiles are not smooth? Now this says smoothed, but it's smooth. What problems are created when mortar joints between flue tiles are not smooth? So let's think about that. When things aren't smooth, what happens, right? We just talked about that with the smoke chamber. Remember the corbelling? That's not a smooth surface. It created turbulence. When we have turbulence, we slow down the flow. So if we have flue tiles going up, terracotta flue tiles that are going up, and that transition from one tile to the next tile is not smooth, what happens? The answer on here is
Smoke residency.
it's what?
Oh, it causes turbulence, which adds to smoke residency in the flue.
Yes. So it adds turbulence. With turbulence, it slows down the flow. When we have a slower flow, we extend our residency time, right? So if from tile to tile seems like it would be smooth, but the mortar joint bumps out into the flue, that's the turbulence point. If the knucklehead that built it offset the flue tiles by a half a tile, that's going to create turbulence, reduces the flow, increases residency. So that's something to remember. Flow is the exact opposite of residency time. Now, not in length and not in quantity, but the higher the flow, the lower the residency time. The lower the flow, the higher the residency time. So we can almost flip-flop those out, right? And then draft is what runs everything. The amount of pressure creates the flow, reduces the residency time. Lower pressure, lower flow, longer residency time. Okay, so I know we didn't have a very big crowd tonight, but the people that did show up are the people that obviously want to be able to pass this test on the first go around. And I know this was kind of me stumbling through this whole process for this one, but I want to thank everybody for showing up and asking questions and everything else. We will pick back up next Thursday. I've got it marked on here which one we're on. In the meantime, let's keep working on the Quizlet stuff. Next time around, I would like everybody to kind of have some questions that they've seen in the Quizlet that they would like a better explanation to. And I want to not just know the answer to the question, I want to know why. Because if we know the why, that can probably help us answer other questions, like the one about the smooth purging on the smoke chamber. is linked to the non-smooth flue lining with the terracotta flue tiles. So everybody, you have a great night. We will be back Thursday at 6 o'clock, and we'll go 6 to 7 then. And we will learn together, and we are all going to make straight A's on this test. All right. Bye, guys.